No, there's one. Oh, no, let's go.
No, no, I will go there. Hi, Tom.
Hey, how are you?
Fine, fine, and you? So
Yeah, really well, thank
they decided that I will be the president of the jury. Okay.
you. Very good.
Hi, Jose. How are you?
Hello, Tarek. How are you?
Fine, fine.
Excellent.
Okay, so we will start in 1 minute. Okay. So it's not easy, maybe, to talk from my desk. So we'll start. Yeah, Andrew will do his talk. He will have a 45 minutes presentation that will be followed by questions. I will start first with Tom, and then you, and after that is Simon Lacroix, and after Simon is Eric Marchand and Ezio Malice, and at the end I will, because I have a lot of power as a president, I will ask him some hard questions.
Okay.
Okay. So we will start now with the. So you have 45 minutes to do your talk on your research.
Okay, so thanks, Tarek, and good morning to everyone here. Good evening to Tom and maybe my family back in Australia who is connecting onto the YouTube channel. So today I'm going to present my habilitation, which is based on all my work since I joined the CNRS in 2007, and I've tried to group a set of works around the topic of visual SLAM and the direct approach to visual SLAM. So what is visual SLAM? So simultaneous localization and mapping is kind of a long-term problem that is about two things. One is estimating the pose or the position and orientation of a sensor with respect to an environment. And the other is estimating a representation or a map of that environment. And if we do that visually, we're doing that with a vision sensor. So there's a bit of a historic for these SLAM approaches that dates back to 86 in the case of laser type measurements. And with vision, we have the computer vision community that started to tackle similar kinds of problems with what's called structure from motion. And it wasn't until around 2002, around when I was doing my PhD, that the first real-time SLAM approaches started coming out. So these approaches were all initially based on features or primitives that are extracted from the image and then doing matching. And the contributions that I'm going to present here take an alternative approach, which is based on using what's called the direct approach. So we call the direct approach an approach that seeks to avoid any feature extraction from the image or any matching, and does estimation directly based on measurements in the sensor space, whether that be a monocular camera, a stereo camera, a multi-camera system, RGBD sensors, or other types of sensors. We're seeking to develop the model and the error directly in the sensor space. So I've grouped in my HDR report all the contributions into several chapters and sections. So one of the contributions is based on modeling different types of sensors and how to integrate that into a direct approach. There's another part which is focused on the localization problem. So in terms of localization, we look initially at visual odometry using only images, and then we look at how to integrate depth sensor information into that as well using RGBD sensors. And we also look at how to make the localization high speed and how to perform loop closure. And in terms of mapping, We have different representations that we have looked at. We've mainly used what we call a keyframe graph representation, but we've also compared to volumetric approaches and surface space approaches. And we've also looked at how to make the mapping HDR, so it's not habilitation, but high dynamic range, and super resolution and semantic mapping. And throughout all this, one main part of SLAM is being able to do it in real time. So there's been a lot of software development efforts behind the scenes that have gone into making all this run at frame rate of a camera, doing all the computation on parallelized hardware such as GPUs, etc. So I thought I would just start with a video to give you an idea of the end product or what we're trying to do. So this is an example of RGBD, so color and depth SLAM. So in the top right, we have the raw sensor information, the depth and the color. And on the left, we can see the map being built incrementally as we wander through an unknown environment. And on the bottom, we can see the prediction from the map. So we're trying to predict the current image from the map. So we have a depth sensor measurement and a color prediction. And we minimize the error between those to be able to estimate the unknown parameters in the system. And you can see here, so this is a map of the lab here. When we get back to the same position, we have a loop detection algorithm running. So we're going to detect where we are. We have a certain amount of drift. So we close the loop and we correct the drift throughout the map to be able to take that lesser error into account because we have revisited a location we knew previously. And so once we have that, we can start doing processing to get sort of different types of 3D models that we can use for different applications. So in the continuity of the introduction part, I thought I would just present some of the major projects that we've worked on during these past years. In particular, we have projects on autonomous cars that we worked on with INRIA initially when I first joined the I3S. And we currently have a project with Renault Software Labs on that topic. We had a DGA Rapid project with Echo Robotics on uneven traversal of terrains. So that was during the Fukushima power plant disaster. And the aim was to be able to guide robots to get through rubble and different non-flat areas, which were difficult for robots. And more recently, we had a project, a European project on humanoid manufacturing with Airbus. So I'll show you a few videos of those different projects. And another axe of applications for these real-time SLAM is augmented reality or real-time human-computer interaction, where you also need to have the location of your sensor with respect to the environment to be able to overlay virtual objects into the scene in a seamless manner. So I'll also show you an example of that. So this is the video of the project, humanoid project, European project. So you can see here the HRP4, and this is our software running on the HRP4. And the goal of this project was to perform closed loop feedback, full body feedback on the humanoid robot. You can see here the line on the ground, the positioning using only vision is close to millimeter perfect. And we need to have those maps to be able to correctly position the feet, to be able to climb the stairs from the shop floor. And then we have to traverse the shop floor to be able to get to pick up a bracket. And then we have our colleagues from REN, which were using model-based tracking techniques to grab the bracket and place it on the fuselage. And all this was running in real time. So this was kind of first prototype system where there was a humanoid robot in a Airbus manufacturing environment. So potentially this could be sped up to do higher speed manufacturing as they do for the car industry, but with mobile robots that can move through the big planes. So I'll just skip through a bit here. So here you can see the grasping of the object and placing of the object on the fuselage. there were a big group of partners and another team that was using the Toro from the German Space Agency to do similar things, but they didn't have the vision part. They were using markers that they placed on the environment. And you can see we're doing multi-contact interaction with the fuselage. So we actually need to have a dense map of the environment to know where different things are we can place the hand on or place the feet on in the environment. So this was a project with INRIA Sofia, where we looked at autonomous driving. So this was using the stereo mapping. So we drove the car through the Place Jaune in Clermont-Ferrand and created an initial keyframe map and using stereo pair. And then we navigated the vehicle using monocular vision. You can see it's in a real world environment with pedestrians and people walking around. This was back in 2011, so before all the autonomous cars started coming out, such as Tesla. And we have a laser sensor just for security. So mainly it's vision only. It's just a laser sensor to make sure if an obstacle walks in front that it will stop. So you can see here, it's able to handle lots of noise and outliers with respect to the map and locate the vehicle and send the control back to the vehicle to follow the path that was planned. So you can see here just the obstacle detection running, bystander walked in front. And this is the other application I was talking about, augmented reality. So in this case, we have 3 virtual objects. You can see the teapot and the 2 bowls. So they are drawn virtually into the environment to look like they belong to the real world. And you can see we have mapped we've made a map of the room here, and we're able to do the reflectance mapping of the virtual objects such that the room is reflected correctly into the objects. And we also detect the lighting positions and project shadows, so virtual shadows, onto the real environment to make it look even more realistic. So a last application that I wanted to talk about is the creation of this startup company PIXMAP back in 2015. So I created the company with a former student, Maxime Mayand, and an external partner, Benoit Morisset. And it was very, basically the transfer of lots of research at the lab for many years. And the technology was getting to a point where it was mature enough to be running robustly in real time on different platforms. And so during the first part of this creation, we managed to get a multi-million-dollar investment in the company. And we spent a lot of effort on marketing, on the deployment of the software onto different types of platforms that you can see here, the drones, personal robots, service robots, and even mobile phones. And we also worked a lot on the documentation API to make it usable via, for third parties. So this was a marking point for my work during the last years. And of course, all of the work that I'm presenting now is not done by myself alone. So I have worked with a certain number of PhD students over the years. 4 PhD students have successfully defended their thesis. And we currently have a certain number of PhD students that are working on the future projects and objectives that I will present at the end of the presentation. And there are also a certain number of postdoc students. So we currently have 2 postdoc students working on a European project for digital storytelling and augmented reality. And we've worked with a different number of industrial partners over the years. And of course, in terms of academic collaboration, we have had a certain number of collaboration with different partners with different publications. So that's the introduction. And now I'm going to present to you the rest with a bit more detail on the technical aspects. So in the first part, I'm going to present the localization. And I'll start with the color before moving to color and depth, and then look at high-speed localization. And then I'll move on to the mapping part. So I'm going to look at large scale, how we do large scale mapping densely of scenes. I'm going to see look at how we integrate the high dynamic range into the map. Also, we'll make those maps super resolution, and we'll introduce semantic mapping. So we'll know about the different types of objects during the environment. And then I'll present to you some of the future objectives and the current projects we have underway. So what's the difference with the direct approach compared to feature-based? So this is just a diagram that tries to summarize what that difference is. So you can see here on the top figure, you have two images input. One is the current image of the camera, and another is a reference image, or it could be the previous image that you had in your video stream. And from those images, you perform feature extraction, and you hope that your feature extractor is invariant to different types of changes in position of the camera or illumination, etc. And then you perform matching between those features, and you minimize an error between those based on the unknown parameters in your system to estimate the pose or the environment map that you're looking at. In a direct approach, what we try to do is avoid the intermediate feature extraction and matching, so that we're minimizing an error directly in sensor space. And we find that to be much more robust. We're using all the pixels in the image instead of a few sparse set of features. We're able to get dense maps from that. It's also more accurate because we're able to minimize any feature matching and extraction errors. So this is kind of the base hypothesis that we have for all direct methods, which is the brightness constancy assumption. So it basically assumes that given a point in space, if we look at it from different points of view, its intensity as seen by a camera will be the same. So if that's not true, which is not the case for all types of surfaces, sometimes we have specular reflections or different surface materials, then that may start to break down. But in general, we find that this assumption is quite valid. And so here we have the idea that if we know image and a certain number of pixels in that image, and we have a second image, and we know the disparity or the shift in that pixel between the two images, then the intensity will be the same. So that's the base hypothesis that all the direct approach is built upon. And then we try to do that. So here we've looked at two images. If we want to do that at larger scale, we start having to deal with more images as they come in. And what we want to do is estimate the pose between a reference image. So we're going to choose a reference image somewhere in the sequence. And then we're going to estimate or minimize the error with respect to that reference image. So that reference image could be considered to be our map or our 3D model, but it's very local at this point until we start building up more reference images. And we have, therefore, two poses, T hat, which is the pose up to time T-1, and T, which is just the incremental pose that we're estimating with respect to the next image. So this is kind of a broad overview of this optimization function that we minimize. This is the error we minimize. We minimize the difference between a reference image I star and the current image I. And we minimize the directly in image space, so the gray level intensities. And we transform, or we perform novel view synthesis of the current image. So we're able to transform it to see what it looks like from a different point in space, as long as we have information about the depth of the pixels or the geometry of the scene and the pose of the camera. So those are the parameters here, T and Z, that allow us to do that. And we do that robustly with this function rho, which allows us to put weights on pixels if they are outliers. So this is just an example of the early work that I did during my postdoc at INRIA. So here you can see we're estimating the 6 degrees of freedom pose of the car traveling around the roundabout uniquely from a pair of stereo images. So we're only using the intensities in these images, and we're able to estimate the 3 degrees of translation, 3 degrees of orientation of the car as it goes around the roundabout. And you can see as it gets back past the same point, that the drift or the error is quite small. So it's very accurate. And you can see that there are moving objects and things like that in the scene. They're being rejected by robust estimation. So I have a small video here of the robust estimation. So you have, again, the input images, and you can see the bottom images here are your warped images or your transformed current view. And so the current view tries to stay static close to the reference image, and then it will jump. And when it jumps, it's when we're taking a new reference image. And you can see as we get out of the field of view, we need to add in more reference images to be able to map different parts of the environment. And at the bottom, we can see the robust weights. So anything that's black is being rejected from the estimation procedure. So that's the color part, if we're using just the intensity information in the image, but around, I think, 2009, 2011, around then, the first depth sensors, real-time depth sensors started to appear. So they started providing directly measurement of depth using active projective light and stereo triangulation with infrared sensors. So we worked on developing an approach that minimized both the color and the depth error directly in the sensor space for both of these types of sensors. And we found that most people just had an error term for each type of sensor. And we found that if we created a common measurement vector, M, and put both the 3D point from the depth sensor and the intensities of the pixel in the measurement vector, and we minimized a point to hyperplane ICP objective function. So that means basically we minimize the difference between the reference measurements and the current measurements with their warping function. And if we project that error in the direction of the normal of the surface, so we create a surface in 4 dimensions here. And by projecting the direction of the normal of the surface, we find that we are invariant to the scaling factor between the two sensors. So that makes it easy because we don't need to tune or have a arbitrary parameter that will give more importance to one sensor or the other. It will be automatically done via the uncertainty of the sensors. So this is just an example of the nonlinear iterative estimation loop using RGBD sensor. So you have as input a reference sensor, and then you have the warped or transformed current image based on the last estimate of the parameters, which creates an error, an image error you can see here. So we can verify nicely from the error. And then we have iterative gradient descent by inversing a Jacobian. And we have the robust weights. And you can see on the right here, just between two images, the convergence of the translation. So 3 degrees of translation, 3 degrees of orientation. And as we iterate and descend the error function, we converge to the true value. Of course, we also want to make this run in real time. So we have lots of different tricks. One of them is using multi-resolution pyramids. Another advantage of multi-resolution pyramid that allows you to make larger the domain of convergence of your local estimation algorithm. So we will start at a small resolution and first estimate the pose at that resolution and then propagate it down and refine it gradually until we get to the highest resolution and the finer detail. So this slide is just about the high-speed localization. So as we were modeling we were doing SLAM with these RGBD sensors, we noticed that if we move very quickly, it would break down. And we started to see that there were all these deformations going on in the sensors because they use cheap CMOS rolling shutter sensors that acquire the first line first and gradually move down. Most people don't move around with their sensors too much, so that's okay. But if we're moving around, it will break down. And we also found that also simultaneously with rolling shutter deformations, we have motion blur problems. So we set about to model that and integrate that into the visual odometry or the visual SLAM pipeline. So you can see here a simulation where we have different global shutter, motion blur, rolling shutter, and motion blur. And you can see basically if you're moving the camera sideways, your image is going to be slanting. If you're moving up and down, it compresses and decontracts. And if you do some sort of screw motion, you will get nonlinear deformations in the image. And so we simulated all that. So here you can see the nonlinear curve here. And then compared it to the classic algorithms without the correction. And we're able to show that we're able to keep tracking and we're able to have much higher accuracy due to that. So this work was the basis of some work we did with Tom Drummond in Australia, and was also part of some patents that the CNRS put down. So that concludes the first part on localization. Now I'm going to switch to the mapping. So the first part is how do we do large scale mapping? So the idea here is if you want to go around and map your environment, if you just have a perspective camera, then you need to kind of wave it around and cover all parts of the environment. Whereas if we have a spherical system, we can start to capture simultaneously all directions. We don't have to worry about waving it around. We can just worry about moving through the environment. So we started to work on this keyframe graph representation where we replaced the keyframes by spheres. And this is kind of similar to the light field mapping, where the light field is basically every point in space has every direction of light coming in. And so this is kind of subsampling the light field when we're mapping the environment in this way. So if we look at one of the keyframes, we have again the color and the depth information. We can also have other information such as saliency or semantics that I will show you later. And with INRIA, we built a multi-camera system, and we purposely made a stereo baseline. So it's a bit different from the Google Street View, whereas in this case, we have the possibility to do triangulation and mapping from the stereo pairs. Whereas Google Street View, you're stuck in your spherical panorama and all the center of projections they seek to be at the same point. And then we perform again our direct estimation on these images for all the different multi-camera systems. So we have several cameras now we're minimizing with respect to. And then we've worked a little bit on how to choose the keyframes, how to place them in the environment to have optimal map from this keyframe representation. So we want to basically be looking at the statistics of the estimation and knowing where we're going to be localizing better by placing the keyframes correctly in the environment, whilst also covering densely the map of the environment. So I just have a little example here of this. So this is kind of like a video game. We've performed this mapping with the spherical system, and we have the poses between the keyframes that we've estimated. We have for each keyframe the color and the depth, and we can kind of just run around like in a video game in real time and render these images by performing novel view synthesis with respect to the closest keyframes. So you can see it's a local approach, but for robotics or for navigation applications, we don't necessarily need to have the 3D map from the sky. And it's much more compact and efficient to be able to represent the environment locally around the trajectory of where the scene was acquired from. So this next part is questioning two big ways that have been used to do 3D mapping. So one of the key points in SLAM is the representation. How do we represent the 3D map or the environment? And the approach that we have taken has been this topological keyframe graph, where we have poses between keyframes. And there's another body of research that looks at voxel-based approaches, where you divide up, kind of like extending image pixel to 3D, and you divide up the 3D world into little cubes, and then you can use those cubes to find the surfaces using sign distance functions and matching cubes to be able to extract surfaces from the environment. So you have different types of representations. But all these representations share a common framework for the SLAM problem. We're still doing sensor pose estimation to be able to determine its position with respect to the 3D map. And there is the transformation or warping of that to project it to the current image. Then we perform estimation between the current image and the transformed 3D map or 3D model. And we try to iterate and update that map also. So we said about comparing it. So here we have the voxel-based approach. So what's nice about the voxel-based approach is it is a unique map of the environment that doesn't have any redundancy like keyframe-based approaches. We can easily extract meshes, and the only problem is we're projecting the sensor data into 3D space and kind of throwing away any information we had about the trajectory from which it was acquired and the uncertainties, and we're linearizing that in this 3D space. Whereas the keyframe-based approach, we have this sensor-based accuracy where we're not throwing away any of the information and blending it in some 3D world. We're keeping it directly in sensor space, and we're still keeping the trajectory and the uncertainty we have about the uncertainty in that. And it also allows us to efficiently perform loop closure and adjust it without having to question or re-put into question all the cubes like you have to in the voxel-based approach. You have to redo the whole map for that, whereas you can just adjust the pose between the keyframes for this approach. The problem is you have redundancy between the keyframes, and the keyframe positioning is not simple to do to have some optimal representation. So we thought about trying to tackle that. So here you have the classic keyframe with the color, the depth, and the pose. And then you have a map, which is a graph of keyframes with some partial overlap between the keyframes. And so basically when we register, you have the current image here. What we've classically done is we choose the closest keyframe to that. So you can see when we have partial overlap, so we don't fully densely have all the information available in the image. So if we want to solve that problem, we could start using multi-keyframes. So we choose n closest keyframes closest to the current one. So here we have all the others. So we have dense overlap. So we're using all the pixels in the current image, but that is very computationally expensive. We're actually multiplying the errors and all the computation by the number of keyframes. So what we proposed was, instead of doing that, we predict a virtual viewpoint at t-1. And so we choose the n closest keyframes. We warp each of those, or perform novel view synthesis to the virtual viewpoint at t-1. And then we do graphics-based blending. So we blend the color and depth images together to create a predicted reference frame from which we will minimize the error with respect to the current keyframe, the current frame. So once we have this keyframe graph with multi-keyframes, we have to maybe be able to manage how we put new keyframes in to be able to have maximal coverage. We also have to perform graph management and bundle adjustment. And we also have to be able to fuse and integrate all the new information into the keyframes so that they become optimal keyframes, not just an image from the environment. So we're going to be integrating all the map information into these keyframes. So this is an example of this multi-keyframe approach. So you can see here now in the top left, you have the current frame, which is connected to multiple frames now, and it's densely predicting the current image. So we're not having this partial overlap anymore. We have fully dense map of the environment, and we can then know also when we need, more easily, where we need to place the new keyframes in the environment. So after that, we set about trying to improve the quality of the maps. So The base sensor resolution 640 by 480 for the Kinect type sensors. And so what we want to do is do like classic super resolution, which basically was done previously in photography, where you take several photographs together and then you combine them to try to predict a higher resolution image from that. But in this case, we're now having a moving sensor, and we have this novel view synthesis. So we're able to then take several images from different viewpoints in space instead of the same viewpoint, and then blend them together in super resolution approach. So this is the image generation pipeline, which is a little bit different than the classic super resolution pipeline, which seek to do an inverse pipeline. Here we're doing forward generation to be able to do this in real time. And so basically we're taking all the low resolution images and we're warping them and combining them together. We're upsampling, we're performing inverse blur before getting the super resolution image. And one of the tricks that we used to be able to do that was to define a distance function from the super resolution image that we wanted to acquire with respect to the low resolution images. So if a low resolution image was closer to the resolution wanted for the high resolution image, then it had more weight than if it was further away. So that allowed us to have a weighting function that allowed us to fuse or weight which low resolution images were more important. So here we have an example of this. So here you can see the base resolution image, and if you look closely at the text, you can see that it becomes more net after the fusion onto the keyframe. Here we just zoom in, and you can see the text is very hard to read, but after fusing several low resolution images into it, we were able to obtain this super resolution image, and we get the same thing for the depth map. Here we can't see the coin put on the table, and after integration we can see the coin, so we're getting much more accuracy out of that. Another extension we made was high dynamic range mapping. So normally our keyframes are between 0 and 255 grayscale levels. But if we're moving through environments that have changing illumination conditions, if you want a very sunny outside day, you don't want to have your exposure time very long. If you want to go indoors, you want to have your exposure time a lot longer. And so the cameras can automatically manage that, or we can manually manage the exposition of the images. But basically we have what's called the camera response function. So you have the incoming energy or irradiance coming from the scene, and the sensor then transforms that into a intensity image. And within that camera response function, you're going to have the optics. They're going to be doing something to the energy of the light that's coming in. And you're also going to be having the exposure setting that's going to take different amounts of energy. So potentially you could have the same amount of energy coming into the image, so the same intensity, with different exposure settings and different lighting from the outside. So if we want a high dynamic range image, basically we're going to be seeking to obtain the irradiance or the energy of the environment in our map instead of simply the intensity. So this is an example of the camera response function, where you have the exposure time and the gamma response, which is related to the optics. So you can see here different exposure settings. And basically what we do, we do this dynamically and map into a high dynamic range keyframe. So this is an example of a fused high dynamic range image, low dynamic range images into a high dynamic range image that's been tone mapped for the screen presentation. But ideally, we want the map to be minimized with respect to, so we again have our low resolution minimization function between reference image and current image. And here we modify the intensities. We actually minimize in irradiance space so that we're able to deal with different shutter values along the way. So I'll just show a picture or a video of this. So here you can see, as we're mapping the environment, the the shutter exposure time is varying. And so we're integrating that into the keyframes. And we have different parts in the office that are brighter or darker. So if we go and look at the lights, it's much brighter. We don't want it to be saturated. And if we go under the desk, we can see on the bottom left here, it's very dark. That's due to the screen. The screen is not capable of showing high dynamic range, so you can't see it. But if we readjust it so you can see the low dynamic range prediction, it's quite similar to the current image. So this solves a lot of problems when we're dealing with varying illumination conditions, which kind of happens quite a lot. So you can see here, after we've done the map, we can then play with the projection of different parts of the dynamic range manually to choose which part of we want to display. So then we perform some semantic mapping. Basically, we performed, we had an encoder-decoder architecture to perform semantic mapping on the NYUD dataset. And we adapted that to the Airbus digital mock-up model, which we used to be able to label and segment in real time different parts of the Airbus model to be able to know where the robot could touch and have identification of different parts of the model. So we rewrote the SLAM problem to be doing that on semantic images. So in this case, we're minimizing the error with respect to the labels that we're seeing in the image rather than the intensities or the depth. And we perform that simultaneously in real time. So you can see here, as we're creating a map of the environment, we're also able to create the labels of the objects in the scene and have more higher level knowledge about what could be done interacting with those objects. So that ends the part on the technical part. And now I'm going to take 5 minutes just to talk about future project and perspectives and some conclusions. So for me, the project that I put forward in my thesis report is focused around spatial intelligence. So I think that what needs to be done from now in the future is to work more on making these real-time localization and mapping approaches, using them to give some sort of spatial intelligence about what's going on in the environment for devices, whether it be mobile phones or for different types of robots. And the idea is to be able to make that in a generic way that can be shared amongst everyone. So it's kind of like an internet of 3D maps that you can interact with. So you can have different types of robots or different types of sensors all contributing and updating maps as they evolve dynamically over time. And then they can use that information and download it in bite-sized chunks or keyframes that they can use to locate themselves or perform intelligent tasks within the environment. And to start that, we've got several projects underway at the moment. I've chosen just 3 of them. So this first one is with Renault Software Labs, where we're looking at doing real-time prediction around the car. So if we have sensors, camera sensors pointing outwards all around the car, or just one sensor looking forward, we would like to be able to predict the future map. So not just predict the image at t-1, but at t+5. So that's what we've done in a paper we submitted recently. So you can see here on the left, we have the incoming stream of images, and we are trying to predict a target image at t+5. And we have this ground truth data and the forecasted depth that we're trying to predict and the error between the two. And then we did a similar thing. We started realizing after that first work that we're only considering the rigid scene, which is what I presented you up to now. And in another paper, we're actually segmenting and detecting instances of objects that are moving in the environment. So here you can see, if I play the video, you can see the different cars being detected. And so as we're moving through the environment, we're trying to predict the depth and also take into account the prediction of the moving objects. So we're actually estimating the pose and doing SLAM using neural network architectures. And you can see that the predicted depth is quite nice. And we have the error with respect to the ground truth. So this is another project, which is a European project for digital storytelling performing augmented reality. And our role in the project is to do large-scale mapping of Lisbon, Barcelona, and Paris. So we built this backpack with a spherical stereo system on it, and we're performing SLAM using this 360 stereo localization at the moment to start to fake GPS data and upload it to the crowdsourced Mapillary app, which is kind of like a crowdsourced Google Street View app. And then we have a last project where we're tackling the representation problem again. So I talked to you about this volumetric representation and this keyframe graph representation. Well, here it's a neural network architecture that's representing the scene, and it's doing it very nicely through novel view synthesis, and all the weights of the network basically store the map of the environment and provide for continuous interpolation between the different things that have been seen by the cameras. So you can see here an example of some of the work we've been doing to do that. So in conclusion, so I've presented an efficient, accurate multi-keyframe graph representation for doing large-scale SLAM with loop closure map correction. And we've done that robustly, accurately, and efficiently. We have proposed an approach to make that much higher quality through super resolution in real time with cheap low resolution sensors. We've shown how to do high dynamic range mapping to handle varying illumination conditions. And we've also done high speed mapping. So thanks for your attention.
Thank you, Andrew. So we will start by the equations. Tom?
Maybe you give me just 1 minute and I'll try to switch over to the conference system in the room.
Yeah.
I just have to connect. So I'm going to stop sharing for the moment.
You are in the meeting now.
Can you hear us?
Seems okay. Okay.
Hang on. Just have one speaker to mute.
There is an echo, Andrew.
Yeah,
You maybe need
No,
to mute
no.
your original device.
So I'm just going to put up the volume on this one. So can you say something just to test the volume?
Okay, does that sound okay?
Yeah.
Yep, that's good.
Yeah, perfect. So you can start, Tom. Oh, okay. Thank you for the presentation, Andrew. It was very interesting to see that detail about what you've done. I'd like to ask you some high-level questions. So high level, clearly you've been pursuing the direct approach as the, I guess, the organizing principle of your research. Why do you believe that's the right way to do things? Why is it better than using key points?
For me, it comes from maybe some of the intuition that I learned during my PhD with François Chaumette and Eric in Rennes, where the visual servoing approach that they were using had a very strong focus on image-based error. And for me, that intuition kind of has also come through from their teachings, but also from the results of trying different things, where you can see a lot of the simplicity, even in the programming, that comes about by using a direct approach. I mean, during my thesis, I was working on features and CAD models, and the whole system, I guess you know very well, but the whole system is very complex to manage in terms of software, and we had a very bloated object level description with inheritance for different types of generic primitives, and then debugging all that was very complicated. So when we moved during my postdoc to the direct approach, everything just became so much simpler, because we were just dealing with pixels, and they're highly parallelizable as well to make more efficient computationally. And then again, like naturally you're using all the information in the image, so you're not throwing anything away. So you can hope to have some higher precision through use of more data. And also you have more robustness, because statistically the statistical properties of your estimator become better with more information as well. And you're not subject anymore to any kind of low-level error where you need to design your features to be invariant to these transformations. They can be included directly in the model. And I think that's the way a lot of the neural network approaches, end-to-end learning is going now, where everyone is doing is trying this end-to-end approach for these same reasons.
Thank you. So you have, I guess, elegance and efficiency, maybe some speed up, more robustness, maybe more accuracy. Now a forward-looking question. So you talked about the things you're going to do, and those seemed like good instances, but I'd like to ask you, what's the driving idea? So what is the light on the hill that draws you? What is the grand challenge?
But for me, the goal is trying to be able to make these robots or these devices intelligent. And to give that intelligent, I believe strongly that having some sort of awareness of space and awareness of where you are in that space, and having a map or having some sort of knowledge about the objects that you see in that space is fundamental to building up that awareness. And the fact that we're trying to do it in real time brings this right into the consciousness level of intelligence as well, where you need to be able to react really quickly and provide information really quickly to be able to provide smart decisions for different agents. So that's kind of the motivating factor, I guess, for the future work.
Okay, thank you, Andrew. That's me.
Thank you.
Thanks, Tom.
Sorry.
José?
Okay, thank you. Thank you for inviting me. I'm really sorry not to be able to be in Nice, which I would have loved to be. And I'm very impressed by your presentation and the work that you have done. There's so much good stuff that has come out of your research, and I'm very impressed. My question is related to actually, I always try to think of what is my biggest fear, or what is my biggest problem that I'm going to face in doing some research or in testing my systems. So I wonder, what is in your opinion, the biggest challenge that you could face? What kind of environments would be constitute failure modes for the ideas that you want to try?
That's a good question.
Can I ask to be more specific? Can I ask? So, what is the failure mode for direct methods? In which real situations of interest you couldn't assume constancy in illumination?
Okay, so for the constancy in illumination, of course, if you have like lots of windows or reflective environments, then
right,
that of course breaks down. But there's a lot of work being done on that actually with this neural radiance field architecture. And it's actually something that we already worked on with Maxime before we did the startup company, but we never published, which basically uses this keyframe approach. But instead of choosing multi keyframes, you actually use the keyframes that have the same orientation as your current sensor. And so you're able to then create view dependency keyframe maps that are able to take into account these different environment properties. But this neural representation is kind of very nice because it's a very continuous representation, and it actually learns how to do the interpolation or give that continuity between the different views that have been acquired. And you're able to index it with even time of day or night or the winter or the summer and things like that, and integrate long-term properties into it. So I think maybe the problem of image constancy is not one of the biggest challenges. I would say potentially one of the biggest challenges at the moment is really being able to efficiently model non-rigid scenes. And that's something that I've looked at many times through the years, whether during my PhD, I looked at articulated object tracking. At the moment, we're looking at using neural radiance fields to do non-rigid human body biomechanics capture. But the problem is with having the right number of constraints for your system and being able to be efficient and doing that in an elegant way, not just stacking together lots of different approaches to be able to make that work with like skeleton models, etc., having something more general. So I think that's one of the big problems that needs to be cracked is getting rid of this rigid world or rigid object assumption and have something that's more general and generic to handle that.
Right. Okay. So so I've noticed that you have always had the idea to address large scale environments, doing it in real time, and also very dynamic camera motions. But what about highly cluttered environments? So, for example, the Charles de Gaulle Airport in high season. How challenging is for these methods to tackle environments where most of the pixels are actually moving in different directions?
Yeah, so that's this non-rigid problem,
but it's a little bit more than non-rigid, because this is what I mean is, you know, people walking around or a lot of cars in the highway or things like that. So the static part is really not much of the image, and most things are moving actually.
Yeah, definitely. We're actually confronted with this kind of problem during the humanoid robot manufacturing project, where we basically created a map that we knew very well of the fuselage. We had all the semantics and we had everything working nicely. And then the day where the European Commission came to evaluate the project, we had like 40 people standing around the robot and following it as it walked through the environment. And we had kind of prepared a bit for that. And the way we did it was we actually didn't use the SLAM in the when it was cluttered. So we would be open loop basically while we were looking for an uncluttered area, and basically just avoiding obstacles until we relocalized and found back where we were in the map. But that's definitely, yeah, one of the big problems is cluttered environments.
Yeah, so still a big problem. Okay, and just one last comment. I couldn't help to notice in the project where you plan to map, was it Barcelona, Paris, and Lisbon?
Yes.
The video that I saw is actually using a feature-based method. So I
Yes.
wonder why. Isn't it so?
Feature-based method from Zaragoza, yeah, or SLAM.
But my comment is not because it's from Zaragoza. I'm just curious.
Yeah, well, I mean, that's largely because when we did the startup company, we did basically transferred all the technology from the lab to the company. And when the company got bought up, the people buying it didn't put in clauses. We weren't allowed to continue working on any of that software. So, and it's a very big software development effort to be able to get things back up and running. To be honest, I would prefer to be working with direct methods. But I think the next best system out there at the moment is OrbSLAM. It works very well, and the feature matching is very efficient, and there's all the loop closure and different types of sensors and IMU, and yeah, so we're at the moment using it for the project, but at the same time we have another part of the project that I didn't show, where we're using that localization information to train large scale neural radiance fields to do the mapping of those cities. So yeah, it's kind of a compromise that we had to make to be able to keep moving forward and not spend time redeveloping what we had before.
Okay, so I'm done with my questions. Congratulations again.
Thank you.
Thank you, Jose. Yeah, the last reporter is Simon.
Okay, thank you,
Simon
Tarek. I have an issue because it seems people are quick. I could ask questions for an hour. But I won't.
Half an hour is okay.
Comments first. I have to admit, a little bit flattered that you asked me to review on your work, because I mean, scientifically speaking, your career is way over mine. I'm really impressed by many of your contributions. Some details like dealing with motion blur, rolling shutter, HDR, and what is impressive is that you use this in a unified, homogeneous approach. In your slides, you said, again, we have this equation. Again, we have this equation, the minimization thing which evolves over the concerns you're tackling. This is really impressive. So that's a very neat, wholesome contribution. I think it deserves a book. Maybe not on the way it's written is not for graduate students, I mean, but maybe this is something you could consider. So I'm totally impressed by your career. I don't think I will add any more. Then I have some questions. So I don't have that much time. I will ask questions from one side of your contribution and then the other side. So on the low level side, what about new sensors, innovative sensors? So you played with vision first. LGBT was seamlessly integrated in your approach. What about plane-optic cameras, event-based cameras, multi-echo lidars, full-wave lidars, hyperspectral data, and so on?
Yeah, definitely. I think it would be great to be able to have time and to be able to look into many different types of sensor modalities. Even just infrared would be interesting. We did have some discussions with some companies that are actually designing new sensors and asking us advice on what we would have integrated if a new sensor was to be designed. And for me, one of the missing factors to be able to get more and more towards a direct approach is to be able to have some sort of measure of uncertainty fed back with the measurements. And a lot of those sensors don't provide that where they could be. And I think that would allow us to, again, get closer to the signal. We're also starting a project at the moment with Huawei to look at doing all the low-level image processing in end-to-end fashion. So we would be trying to get rid of the low-level hard-coded image processing and working on all the incorporating all that into the task at hand. Yeah, I think I mean, you have worked much more than me on laser, but I think definitely laser sensors are evolving very quickly as well, and we're getting like even dense maps from lasers at very high frame rate. I think a lot of stuff we did even on rolling shutter deformation correction could be applied directly to a lot of these approaches.
So on this question, but I think I know the answer. If you were given such sensors and given time to work on and so on, would you say again we use our minimization approach? I think so.
Well, yes, I guess. I mean, I still believe in direct approaches. So I would seek to do it as directly as possible. Maybe at the moment, most of the tools we're using in all the projects are deep learning approaches. So maybe there would be much more a flavor of that in the modeling, but yeah.
Okay, so that was on one side. So the input somehow of the system. Now I'd like to speak a little bit about the core, the representation, and which is the best representation. I mean, anyone in robotics has been asking this for decades now. And in your very nice picture, where I definitely buy the thesis that the core of embodied AI, I mean AI embodied in a moving machine, is a spatial representation and the way you present it. I definitely buy this. It's not enough still. In this picture, you know, where we have agent 1, 2, 3, 4, 5.
Yeah.
There's an agent I'm missing. It's a human. There's a workstation, okay, but it's a human like you, me, your grandmother, whoever, without any augmenting thing. Any comment on this, and also on the representation, on the interaction between the human and this representation?
So that's maybe an oversight on the diagram, but I mean, this current European project that we have called MEMEX, based on digital storytelling, the idea is to bring about this spatial awareness and intelligence into an augmented reality app. So the goal is kind of like to do something like a fusion between a virtual museum visit, where you can go through with your phone and see different information about the scene, and a kind of Facebook style blog where people can tell their stories. But these stories would then become geolocalized in cities. So you could be putting yourself into different augmented worlds. For example, you put yourself in a graffiti world and see people that have tagged different parts of the city, or you could be interested in music or arts and have a different experience. So there is definitely that spatial intelligence that coming back to the user as well, I think, through mobile phones, which are evolving very fast.
Okay, but we are stepping into something else than just spatial AI, which is a basis. We are stepping into interfaces between human and these information systems, or collaboration. And hence, we have to move way upper than the spatial representation, which is a basis, agreed. And this comes me for a remark and then a question. There's something I don't buy in your whole work. It's the recent thing where you call semantics lab. The word semantic should not be used at all here, to me. because you use the good word, like, okay, we have a neural network, it labels things. Okay, some say it recognizes things. Semantics is way more, I would say, way more than this. Mm-hmm. Semantics is about relation, hierarchies in the objects, affordances in the objects, relations between the agent, its perception and action capacities, and the object. So when you tag this word semantic slam, I'm sorry, this is not semantic slam to me. So, maybe I hope I'm not losing you. But when we come to interacting or collaborating with human, then we have, I mean, the representation has to match the human semantics. Mm-hmm. And with the human background, the human knowledge, and so on. Mm-hmm. We are way far, we are not anymore, I mean, this is really a new dimension to spatial AI, which we don't have now, mm-hmm. which we are far to have. Any comment on this? You could say BS.
Yeah.
Question.
No, I mean it's right. I mean in the project, the project that I put forward, the idea was to have this kind of shared map of the world. So it's kind of like internet of mapping that you can interrogate via a search engine and interact with, and in different ways. So you could interact with it directly through sensor data, or positions, or spatial elements, but you can also then potentially interact with it semantically via what, when, how, where, or
that's different. A big next step. Okay.
Yeah, that's definitely a huge step. Yeah, and I mean we're starting to try to dig into that a little bit with using these transformer networks to draw temporal relationships between different semantic segmentations of the scene, and maybe I'm not using the right term for that either. But
one comment on one very last question. I'm sorry, but I think you are addressing this next big issue the way it should be addressed. Just like you addressed the spatial mapping down from the pixel, we should address the semantics and the interactions with human from spatial AI. So I think this is the way to do it. I'm not from another, top-down approach. So that's a comment. And the very last question. There's something I'm really missing throughout your work, because you've been dealing with robotics a lot and so on. So we have seen a lot of impressive videos with a hand-moved camera or robotic moves and so on. The characteristics of robotics is to decide their action. And perception is by no means a passive process. So what about active perception?
Yeah, I mean, definitely. I didn't present anything on active perception.
Did you make something?
We have done some work on it. Mainly, I guess, with Christian, who's behind you, on high dynamic range. We actively controlled the shutter of the camera to maximize the information we're acquiring in terms of high dynamic range. But yeah, we haven't kind of gone much further into that aspect. But yeah.
Can I say a last thing? Because it's very interesting, because you active perception is not only viewpoint selection, but it starts, as you just said, like time of integration, shutter control, which I like very much. All the more since we would consider like hyperspectral data, or think that this will come up one day, full wave hyperspectral LiDAR. I don't know when it's come, but you have gigabytes of data in just one shot. It's crazy to process, and it's actually useless to acquire. Then you should acquire actively in these dimensions, and then control the lower level of your sensor up to the viewpoint changes and so on. It's just a comment. So again, I think you're posing the problem and tackling the problem the good way, bottom up. Mm-hmm. Thank you.
Thanks. Thanks, Simon.
Okay, thanks, Simon. Yeah, maybe Eric. Eric?
Merci Tarek. So Andrew, thank you very much for having invited me. You have done a very nice presentation of a very coherent work, I think. The only thing I regret is that you didn't do it 5 years ago. I think, but nevertheless, it was very good. I also really appreciate your document. I remember that you provide me with a 300 pages PhD thesis, and there are 200 pages HDR. I thought when I get it in my hand, it was a little bit too much, but actually, I think it's a very good document and introduction for every people who want to do a direct approach. So I think I will provide it to my student in the future. So I really appreciate to read it. So maybe I had a lot of general questions, but they have already been asked. So maybe I have also some more technical questions. If you don't mind, I will try to ask them. Actually, pixels in the image are highly correlated. And do you foresee a method to use this property in order to reduce the complexity of your problem? Because the main issue with the direct approach is that you have many data. It can be very difficult to process in real time. And do you think it's possible to address this problem by reducing the correlation between processing by I don't know, dimensional reduction process or things like that?
Yeah, so definitely, I guess, like in my work, the parts that look at that problem, I think probably through the multi-resolution pyramid, we have some kind of spatial connectivity going on that allows you to make the approach more efficient. And I think it makes me think about your work, maybe on mutual information that could definitely be used to help reduce the amount of information in the image. We also did some work on through the Jacobian, using the Jacobian to iteratively select the information, but not in a naive way, but in ensuring that the pixels that are chosen sparsely in the image constrain correctly the estimation problem. So it's some things we've looked at, but probably there are other techniques as well that are useful.
Yeah, you just mentioned the mutual information. You never use any other similarity functions than the SSD, or I don't think so, but
we did use the zero normalized cross correlation function at some point, and yeah, we have done some TVL1 for dense stereo matching, but we didn't play too much around with the nonlinear estimation criteria.
So you have used the CNN, I think only for semantic. Do you think it's possible to consider other kind of CNN for mapping or SLAM approach? Because I don't see a lot of paper about that for the moment.
So yeah, I mean, of course, in the work that we showed at the end, we're using something like PoseNet to perform the localization of all the instances and the scene, and to perform the depth prediction. But yeah, it still doesn't work quite as well as the classic approaches. It's not as efficient, and it's dependent on the scene that's been used to train on. So it's not easily can't be easily generalized. But yeah, I think Tom probably has some things to say about that. With work with one of his students, I was on his PhD jury, and he did some nice work on constraining SE3 in latent space to be able to apply these sort of constraints as well.
Okay, so in your PhD, if I remember well, you did a little bit visual surveying. You don't have you don't continue on that with direct approach. Is that something that you didn't want to do, or?
I think it's very interesting. It's just very time consuming as well, as soon as you start getting into the hardware aspects. So, I mean, we did work a bit on it for the project with INRIA for the SciCab and the humanoid robotics project. We spent a lot of time trying to get the feedback, full body feedback with the robot working correctly with a QP, quadratic programming controller, and yeah, it's not something easy to do, and it's a bit more difficult to value the time and investment with that. So that's probably one of the reasons why I haven't done so much visual surveying.
So as for direct mapping, you never deal with a dynamic scene. Is it something that is impossible to do with a direct approach, or if no, how do you foresee to go to that? Because the world is dynamic, is not static. So I think it could be interesting to go there. You already mentioned that to Simon a few minutes ago, but I think it's very difficult to do that because it broke the constant the elimination constancy approach and so on. So
yeah, I mean that's for me, it's one of the hardest approaches. Like we looked at it during the PhD for the articulated objects. I've made several attempts to work on very deformable scenes, including fluid motion, and it all comes down to the amount of constraints you have on the system, and you have this continuity of constraints between rigid scenes and fully fluid environments, and as you lose the constraints, the whole system starts to get more and more unstable and less robust, and yeah, less usable. So at the moment we're sticking with multi-rigid objects and trying still to tackle the problem, but I haven't yet seen a solution that works like perfectly. A lot of people have done some good work on it, but yeah.
Okay, so maybe a last question. So PIXMAP has been sold to a company. I think I found it, which one it is. So it has an augmented reality library, this company. Is your software included in this library or not? Or can we use it? Okay, can we have access to through this library to your software or not for the moment?
Yes, yeah. From what I could tell from the technical announcements for the advancement of this toolkit, there are several aspects that have been integrated into the distributed version, which allow you to handle shadows and do specular reflections and things like that in the augmented reality. So I think parts of it have made its way through. I'm not sure about the full extent of what is used from the main aspect, which is the localization and mapping, because I know just previously another company was acquired that was using to do that using feature-based approaches. So.
And nevertheless, it's nice because it means that tens of millions of people, or if not hundreds of millions of people, may use what you did. So I think it's worth mention it. So. So I have some other technical question, but I think I will ask you in another time. It's very technical, so it's not the place to do that. So thank you, Andrew, and again congratulations.
Thanks, Eric.
Okay, thanks, Eric. So Ezio. Okay, so first of all, I would like to congratulate you for your work, since your seminal work we did in during your postdoc area. You have provided a lot of improvement and contributions, so very impressive. And so a lot of questions have already been asked. So I think I have one which is very technical. I'm sorry. Is when you described in it was slide 34. When you said that instead of doing many warping when you have multiple keyframe, and instead of using many warping to produce to optimize, yes, no, it was 34. 34. My English is not okay. So here you said that you would need many warping, but then just after you say that you make a virtual viewpoint by warping all the key points. So I don't understand. Is maybe because one is offline, many warping are done offline.
So basically, you have a set of keyframes. Yeah. Which are being chosen as being closest to the virtual viewpoint at t-1. And because you have the color and the geometry in each keyframe, you can perform level view synthesis to transform these views to here. So you get these three views that are then blended together to get a complete view for t-1.
Yes, but we're opposing this to the other way to do is to warp each image into the current frame, and you said this will require to do n warping.
Yeah,
but you are doing this n warping as well. So I didn't understand.
This only requires one warp for each of the keyframes, whereas the previous approach is you're creating an error function for each.
Yeah, okay. You are iterating. So each iteration you have to
and you're inversing the Jacobian, and you're iterating over the whole lot. So you're multiplying your whole estimation system. This is just a warping, which is really cheap, and a blending. Yeah.
Okay, I understand now. And then I have a general question. So all direct approach are also have also the hypothesis that when you optimize the high nonlinear function, you are not too far from the true solution. So have you worked on solving this kind of problem when we have large motion between images? For example, if you embed your sensor on a drone, it happened very often that the drone has to change orientation very fast. So the overlap between images is small. And so have you done some work to solve this kind of problems, or you just rely on the fact that you process quickly enough with a high rate, and the overlap will be always small?
So I would say theoretically, we haven't tackled the problem like we could. Probably maybe working with Tariq and Claude or yourself to really tackle theoretically the problem of the convergence domain. So we haven't done that. So we've just used a whole heap of tools in our toolkit to make sure that we deal with this problem. So one is like making it more efficient so that we're running really fast, like technologically, we can run at 1000 hertz on a GPU, this software. So we're largely above the frame rate of the camera. So we're not going to have any problem having enough time to converge. Then, I mean, you have the multi-resolution pyramid, which allows you to try to smooth out and look at more global information, which helps to make bigger the convergence domain. And then we have, in some cases, we can predict if we know the movement of the robot or the car, to help remain close to the solution. And then in the end, if it does end up breaking down, we just have implemented a fast relocalization, local relocalization. So we just detect when we've lost tracking, and then search for it until we get it back. So it's more technological approach to solve that.
Okay, and also I have a last question about your future work. I didn't get exactly what you mean by the internet of I don't know, representation. So it means that because you are mixing humans and robots, so I don't get, because maybe human needs are not the same of robot needs. So, and you would like to do a common representation for both. So can you explain better, because I don't get, because for example, for robots, maybe you need information that humans don't care.
Yeah, so I guess you're going to have some sort of information in the representation that is only going to be useful for humans, and some that is going to be very specific for a sensor or a robot. So that's the non-generic approach part. But for me, it's the spatial AI part that is common. So it is this SLAM, it is this localization and mapping, which provides awareness about what's going on spatially around the agent. That is kind of something that will be common for both. So if we're able to have a very rich map and a very easy way of localizing the device with respect to that, that will form some sort of general framework that can be shared.
Okay, so the user is not directly, for example, a human user is not directly using the representation, is a smartphone or that use the representation. No, it's not visualizing the representation of the human.
Well, it could be. It depends on what they want to do with it. If they want to do augmented reality and they want to have video see-through and have images generated from the map, then they will be using it. If they just want an arrow saying go that way, then they won't. But it's more providing access to this rich source of spatially aware information and techniques to localize where you're at with respect to that, and even feedback and update the map. If you have like cars driving down the street and the parked cars have moved each day, or there's some roadwork sign that's appeared that needs to be integrated into the map, then yeah.
Okay, thank you.
Okay, thanks as you. So Simon has a
quick thing, because we aren't. Okay. You mentioned something I feel very concerned about. You started by mentioning a common representation between the human and the robot. I have no idea of the world representation we do have.
I don't.
But this
was my question, to understand if.
But this representation, or this, I want to, my robot companion, I want to ask him, please, can you bring me back the coffee cup I just used 15 minutes ago? And the system should know which coffee cup I'm talking of, where is it, and so on. It's a matter of interaction or collaboration. But that's all. Thank you, Tarek.
Yeah, since I was lost for the last 10 slides, I can say just it's very impressive. Really impressive. But I have, anyway, you got a lot of high level equations. I have a short one, a low level equation, very short, is about the error that you are using from the current image that you warp, and you do the difference, use the difference between the warped image and the reference one. So why this kind of error? You have other possibilities, right? You warp the reference image and you do the difference.
So, I mean, that comes back to the whole idea of doing direct sensor-based approach. I mean, if you're minimizing with respect to the reference image, then it's different actually for a depth sensor than for a color sensor. If we're talking about just the color sensor, then there is reason to maintain the reference image and not touch it, because for one, it's where we're going to be integrating the information from that we're acquiring over time. So this reference image is going to become more precise and more optimal over time. And if we're warping it to other points in space, then we're going to be introducing the errors in that warping function into the reference that we want to be the minimum of our function. So we want to stay as close as possible to the sensor reading than some other projection of that space. For a depth sensor, it's a bit different because you're invariant to where that is transformed to, because the distance between 2 points in 3D seen from different views is always the same. Whereas the image error is projected in the image and depends where it's been seen from.
Yes, but the error seems like the same in a sense. I have the current image, I warp it to the initial one, to the reference one, I do the difference, or I take the reference and do the warping in the other direction.
But there are approximations made as well in the warping function. So, I mean, if you're interpolating, that's an approximation of what exists, that you don't warp the same pixel to a single pixel. It doesn't fall exactly where you want it. So with the forward warping, you actually have to generate the surface and then interpolate onto that. So all those operations are potential sources of error. It's not perfect transformation. So I don't think the image error is invariant to viewpoint, whereas I think the depth is.
No, I was thinking that the error may be due to the error in the group, because if you do, you have the a t, which is an SE3 element, and the minus a t hat, which is another SE3 element. The difference in the Euclidean space is not easy to do. And when you do the warping of the current image to the reference, you do the right computation in the Lie group, and then when you analyze, is something I don't know, but this is my understanding. Maybe you know this question better than me. Okay, so thanks again for your talk, and we congratulate again the Andrew for his talk, and I ask you to leave the room, and we will stay here to.
So I created another Zoom link.
Is another Zoom? We can stay here and ask people to leave the room, and we stay on the same one.
Yeah, but it's being streamed to.
Okay, yeah.
YouTube.
Yeah. Okay, if it is streaming, yeah, you have to stop there.
So.
Yeah, we change. Yeah.
So
we will stay here. Anyway.
I guess everyone has to switch to the other link I sent this morning, and I will switch over as well. Okay. And then we switch back again after. Okay.